Field volcanologists are not too high-tech. Impressively basic, really. Field volcanology is a bit like being a detective. Sherlock Holmes would have made an awesome volcanologist. Elementary, my dear field volcanologist. Our tools are a hammer, a garden spade, a hand lens, a scale bar, a camera, a map and a notebook. You also need outdoors gear, so you're prepared for the volcanic weather. Could be raining rocks, but most likely it'll just be changing rapidly between hot, wet and windy. We battle through bush to find the rocks. Then we describe what we see in our notebook or on our map and we take photos. You can get some funny looks. People seem surprised that you're not looking for gold, but instead looking for ash layers and drawing rocks. So being a field volcanologist, it isn't hard. You don't have to be a maths whiz kid or an expert in chemistry, but these skills can help. You do need to work hard and to describe what you see systematically and in detail, remembering to measure things as you're going along. So here in my backyard volcano of Banks Peninsula, we'll describe some outcrops of rocks together. Starting from the big scale, how does the outcrop fit into the big picture? Well, I know where we are on the map. Here, near the shore. This is the top of the volcano, so any eruptive flows would have flowed downwards in this direction towards the ocean. So, here I am looking sideways at a lava flow flowing out into the ocean. But from another angle I might be looking end on, or if I was in a helicopter I'd be looking down from above. So then we ask ourselves, are there any layers? As I walk along this outcrop, I can see that there are at least 10 layers, probably more. How thick are these layers? I would say they're varying from 1 to 5 meters. What colour are they? They're light grey, there's some red ones. Are there any giant boulders or big clasts? I can see in this layer there are clasts, and they're between 10 centimeters and 30 centimeters. The number of layers tell you how many eruptions there have been. And if you can find some way to get an eruption date, maybe using radioactive decay of minerals, then this helps you work out what the eruption frequency may have been. So maybe you could use carbon dating. For example, if you do get a carbon date of 100 years old, and there were 10 layers above it, then you can work out that an eruption occurs every 10 years. That means that in any one year, you have an eruption probability of 10%. Here at Sumner, getting the ages of rocks is very hard, as these rocks are 10 million years old, and it can be really difficult to get an accurate age. So if we move on to the smaller scale and try to describe in some detail, is the rock solid rock or is it made of particles or clasts? This one is made of lots of clasts, but this one seems to be solid lava. And in this sample, these particles are mostly less than 1 centimeter and quite angular in shape. Most of these particles, I think, are dense rock, maybe made of lava. To describe rocks, we have our own secret volcanologist language. If we made it too easy, everyone would want to be a volcanologist. So for example, instead of saying that the particles are all different sizes, we might say that the clasts are poorly sorted. And instead of saying that the particles are 2 millimeters to 6 centimeters, we will say that the clasts are lapilli-sized. And if they were less than 2 millimeters, we would say that the clasts are ash-sized. So this rock is poorly sorted with blocks, big chunks, lapilli, medium-sized chunks, and ash, the tiny chunks. And we can even look in more detail. And this is where I need to get out my hand lens. Now I can describe the number and the size and the shape of individual bubbles and crystals within the rock. This way I can confirm that this is a lava. Maybe there aren't too many bubbles, and maybe I can see the small crystals that support the cooling rate that you see in lava. So why is it so important to describe these rocks in this painful detail? And it's because these descriptions tell us not only how many, but also what types of eruptions have occurred in the past. And this is how we can tell the future hazard of the volcano. This is probably one of the most important jobs of a volcanologist. understanding the past to help us plan for the future. Here in Sumner, we can see that there have been hundreds of lava flows and the occasional ash layers. So the hazard 10 million years ago would have been dominated by lava flows with the additional consideration of minor ashfall. And if we were to draw a hazard map, lavas would feature prominently. So thinking about hazard, it's important to consider both the probability of the event, how often, and the magnitude of the event, how much damage it could cause. Here in Sumner, 10 million years ago, we worked out that lava flows and occasional thin ash falls were the dominant hazards. In the next video is from a great location near Mount Tarawera. Mount Tarawera is a lava dome in the North Island of New Zealand, and it formed from sticky gas-rich magma inside one of New Zealand's granddaddy calderas, Okatina. Graham, whose job it is to make volcanic hazard maps, will give an example of how to describe volcanic deposits for you from this medium-sized eruption from Okatina caldera. The description allows Graham to work out which deposits are from which types of processes. For example, did a pyroclastic flow create this deposit, or was it an ash fall or a lapilli fall? At the location where Graham and I are digging in the ash, the thick deposits show that the hazard from falling pumice and pyroclastic flows is very high, as we are within 10 kilometres of a volcano that has had a medium to large eruption.